So we've talked about hydrostatic equilibrium and the balancing forces between inwards gravity and outwards force of gas pressure from fusion. Today we're going to talk about what the actual stages of stellar evolution are. So the progression of a star through its stages depends very, very heavily on the mass of the star. The mass of the star determines how much gravity there is, and gravity in turn then affects how much heat and pressure there are at the core and what fusion it can do. So, depending upon the math, there are a couple different pathways and definitely a couple of different endpoints that a star could have. There are other factors that affect the star's evolution. For example, if a star is part of a binary system where two stars are orbiting each other, that could have a big impact on it as well. Regardless of a star's size, anything that's big enough to become a star starts off as the same thing. All stars start off as part of what we call interstellar medium. Inter means between, and stellar, of course, refers to stars. So this is the stuff that is between stars. So it exists just as a stray atom here and there. It also exists in low-density clouds of gas and dust. Mostly what's between stars are the most abundant material in the universe, which is hydrogen and helium. In addition, we also have some of our common molecules like carbon monoxide, carbon dioxide, water, ammonia, etc., dust, that collects into nebulae, or nebula for singular, and nebula is just a cloud of that. And so there are three kinds of nebula. I'm just going to go through this very, very quickly. I'm not going to ask you to know it. So our first kind is an emission nebula, and an emission nebula is giving off its own light. The hot stars that are inside of the emission nebula excite the gas, and so it's mostly hydrogen gas that's there, it's excited, and it's glowing, essentially. A reflection nebula is, as its name implies, reflecting light from elsewhere. So the starlight from nearby light is scattered by the dust in the nebula, and it's not producing its own light, but rather reflecting light from elsewhere. It has a bluish look for much of the same reason why our sky is blue. The small particles scatter light, making it look blue. The one we really care about for stellar formation is dark nebula. Dark nebulae are dark because they're very dense, and the material in them obstruct the view of more distant stars, so they kind of make a section of the sky dark. They're very, very cold. They're near absolute zero, but it's from there where we can end up getting a molecular cloud that can form a stellar nursery, or in other words, a spot where baby stars form. A dark nebula doesn't necessarily guarantee a star's formation. Something has to happen to that nebula to make it start to become a star. So, within the dense parts of a nebula, something has to happen to make it become unstable. And if it becomes unstable and two particles in that nebula get closer together, they now have more gravity, and that gravity can pull in more material because they have more mass. And so that instability leads to collapse in a star. That instability, that thing causing the particles to get too closer together, could be something like a supernova, could be a nearby explosion of energy due to sudden fusion, it could be nebulae colliding. There's a whole bunch of theorized ideas of what could cause it, but something causes that dark nebula to start to become unstable and collapse. A collapsing nebula begins the very first stages of star formation as what we call a protostar. Proto means primitive or early or first, and so a protostar is the first early phases of stellar formation. Protostars have a couple of characteristics, but one of the most noteworthy characteristics is that they are collapsing and doing what we call accreting. And what I described on the previous slide, accreting is basically just gaining mass due to increasing gravity. So material, as I said, collects. Material's close together now. There's more gravity, which means it can pull in more stuff. So accretion means gaining mass due to this phenomenon. Now, in a protostar, what makes it more than just a collapsing star is that as that gas gets compressed, it starts to generate heat, and as it generates heat, that heat gets converted from gravitational energy gets converted to thermal energy, which eventually causes the star to glow. So in order to be a protostar, it really needs two main characteristics. It needs to be accreting, it needs to be collapsing due to gravity and gaining mass, and it needs to glow. It's notable that while that's happening, the gas becomes ionized. So an ion is a charged particle. And so in that protostar, it's generating enough heat that the nuclei of the atoms no longer have the electrons floating around them. They separate, and we've got the nuclei and we've got the separate electrons, and they're no longer orbiting one another. Now, there's a lot we could go on and on and on about protostars, but a couple of noteworthy things, and that is that within a protostar, there's basically two areas. The core is the center glowing region that's collapsing, and then around the core, there's a disk. And what happens to that disk drives what happens to the star. Does it just become a plain old star? Does it become a star with planets? Or does it become a star that has multiple stars orbiting it? When we look at the HR diagram, protostars don't quite match up because although they are hot enough to generate heat and to glow, they don't make it in to this range of our coolest stars. And so they are off of our HR diagram. They are dimmer for the most part, and they are cooler than what we would see in any of our other stars. The next stage of a star's life cycle is called the pre-main sequence star. Now, a pre-main sequence star is characterized by the slowing down of accretion. To give you an idea of why this happens, imagine you're packing a bag full of clothes. And as you put more and more clothes into the bag, it becomes tougher and tougher to do and start to have to squish it down in there. That's because the material that's already there is kind of giving you some resistance. And that's a little bit like what's happening inside the star. As more and more matter accretes and comes into the star gets denser. And the density of the material, as the interactions between them, the particles are bouncing off each other and hitting each other, and the pressure from that material as it gets denser and denser is counteracting gravity. Now, some stars, as they age, go through a variety of stages. So there's a number of different characteristics that we could have in a pre-main sequence star. Some, like this one in the picture, which is a real picture, will eject matter from its poles. Others, a particular class of stars called a T Tauri star, will actually begin fusion while it's still accreting in the pre-main sequence stage. Now, I don't expect you to map that or characterize that as one of our characteristics of a star, but it is a term you should at least be familiar with. So T Tauri stars start fusion early in the pre-main sequence stars. It typically happens for stars that are smaller, more towards the size of our sun, as opposed to larger stars like, say, Betelgeuse. Remember, a star will start fusing when somewhere in the star, specifically the core, gets hot enough to do fusion. Specifically, it needs to be at 10 million degrees Celsius in order for fusion to happen, because remember, we need to overcome the repulsion force between the nuclei. They're both positive. They don't want to be together. They need to be at least that hot to have enough energy to overcome that repulsion. So some stars go early. Other stars never get hot enough in their core to do fusion. They never get hot enough to overcome that force of repulsion, and they get stuck in basically what is the pre-main sequence stage. They've kind of cleared an area around their nebula of all the mass that can be there. They have gotten hot enough to glow. There's enough material that it's kind of pushed back and it's no longer collapsing, but it never gets hot enough to actually fuse. We call that a brown dwarf, and it's about 8% the size of the sun. So the reason why it's smaller is because smaller stars don't ever get enough gravity to generate enough heat to do that fusion. Most stars, conversely, do get big enough because most stars are larger than 8% of the sun's mass, and they are able to, in their core, have enough collapse occur where they get hot enough to reach the temperature needed, 10 million degrees Celsius, to fuse. Now, the easiest thing to fuse is to fuse hydrogen into helium because that's the smallest element going into the next smallest element. And when a star starts to fuse, that is the defining characteristic of a star, is that it is doing fusion. It's at that stage we call it a main sequence star. That should be a familiar term. We'll come back to that in a second. And it has hydrostatic equilibrium. So a main sequence star is the first stage of the star, It's doing hydrogen fusion in the core, and it's got hydrostatic equilibrium. And just to remind you, hydrostatic equilibrium means that the size is stable because the inward force of gravity is balanced by the outward force. In this case, it's from the density of the material, and most importantly, from the newfound fusion that's been enough to say, hey, gravity, stop pushing out in, or at least stop collapsing, and gravity's always going to be pulling in, but it's enough to balance that force of gravity and to have the size of the star be stable. It's at this point that we consider it a star. You have a diagram like this in your notes. It would be helpful for you to label that in the core here is fusion. Now, I mentioned the core, that's the center part of a star. Around the core is a material matter that we call the shell. And outside of that, we call the envelope. The envelope isn't seen in this picture. The envelope would be like what the surface of the star would be. And the shell is the area around the core. And in a main sequence star, it's the core that is hot enough. Only in the center section is it hot enough to do fusion. I mentioned that it's a main sequence star. That should be a familiar term to you. A main sequence star means that it falls along the main sequence line here on the HR diagram. So that means that the hotter the star is, the brighter it's going to be, and then consequently the larger the star will be. Now on the main sequence, you can see that the main sequence is quite long. And stars don't necessarily move around on this main sequence. Their position along here depends upon their mass. The smaller the stars have less energy, so they're dimmer and cooler. The larger stars have the most energy, so they're hotter and brighter. And the medium mass stars, like our sun, fall in the middle. So all stars will go from being way over here off the HR diagram in the pre-main sequence and protostar stage to main sequence stage. They will pop up somewhere along this line. Now, the star's lifespan varies greatly based on its size, but no matter what size of the star we're talking about, the main sequence is the largest portion of its life. It's about 90% of its life, give or take. During the time on the main sequence, there will be slight fluctuations, but essentially it will have that hydrostatic equilibrium and it will be fusing only hydrogen in the core. The larger the star is, the shorter their lifespan is because it's able to burn through its energy. It's able, in other words, it's able to generate hotter temperatures faster and move on to later stages of its development. So big stars can do that faster, and smaller stars take longer to get hot enough and fuse at a slower rate, and so they last on the main sequence for a longer amount of time, still about 90% of its life. The next stages of stellar evolution happen when the star runs out of hydrogen in its core. We'll talk about most of that in the next videos, but before we move on, there's one more type of star I want to talk about. There's one group of stars that don't run on, and we call them red dwarfs. They're red dwarfs because, of course, they're on the main sequence, on the red, cool, dimmer side, and they're small. And because of their small size, they never run out of hydrogen. They burn. It takes them a real long time to get hot enough, and they burn so slowly that they're not converting hydrogen to helium fast enough to run out. And so they kind of always stay stuck in the main sequence stage. Now, never and always is a relative term because we don't know what happens. Eventually, they will convert all of their hydrogen into helium, but it takes so long that that's yet to happen to any star, and it probably won't happen for many, many millions and trillions, billions and trillions of years to come. And one of the main reasons that happens is because they're not divided into a core and a shell, so they have access to all of the hydrogen in the star because it's convecting. In other words, it's circulating due to temperature differences. That's the beginning stages of stars. In our next video, we'll talk about what happens to lower mass, bigger than red dwarf, but lower mass stars, and then we'll do another video later on higher mass stars.